I'd like to start by thanking the Adalis Foundation and all of you for being here. This is a great honor, and the Weizmann Institute would not be the unique research environment that it is were it not for your involvement. I'd also like to start by noting that, again, that I'm not this year's recipient, but last year's recipient, and we all know why this meeting did not happen last year. Before starting, I'd like to express my hopes for the safe return of our hostages and our troops and for the end to this war. Thank you. Okay. I study Earth systems history, which is the way in which the Earth system has evolved over the past 4.5 billion years or so. One of the things that I like most about my work is that it's a lot like being a detective. The answers don't throw themselves at you, but you have to coax them out of rocks. There should be some rock samples moving around the audience now. And what if I told you that based on analysis of these rocks, I can tell you about perhaps some of the most extreme climatic events that occurred over Earth history? What if I told you that I can learn about some of the most fundamental events that have occurred over Earth history? Okay. So what's the challenge? What's the challenge here? The challenge is that the Earth is a complex system in which things affect each other in subtle and often non-intuitive ways. And it's my very satisfying job to sort of tease these apart. So the heat that's generated in the Earth's interior causes the solid but viscous mantle to overturn. And this produces both volcanic activity and produces Earth's crust. And the volcanic activity puts a lot of gases like carbon dioxide in the atmosphere. And so the convecting mantle also drags along the tectonic plates. It pulls them apart to create new oceans, and it brings them together to build mountains and supercontinents. The mountains then weather and erode, and the products of their weathering make it into the soils and into the ocean, where they stimulate the growth of plants and algae. Now, these plants and algae sustain the entire food web. And when organisms die, they settle to the bottom of the ocean, to the seabed, and a fraction of the carbon that's in them gets buried in the sediments. And so this balance of volcanic outgassing of carbon dioxide on one hand and the burial of carbon in marine sediments determines the atmospheric concentration of carbon dioxide, which is a main lever on Earth's climate. And so you can see how these many interactions, which are really just the tip of the iceberg, can seem like an inextricable mess. And as I said, for me, this is a part of the draw of Earth system study. So the chance to generate clarity from clutter, mechanism from mess. And another attraction is that these processes, which operate on timescales of hundreds of millions of years, set the stage for everything that has happened on Earth's surface. And you can think of them as the reason that the Earth has remained habitable for more than 4 billion years. And this is not an easy feat if we judge by other planets in our solar system and beyond, which are inhospitable to life as we know it. And of course, we can't directly observe the events and the processes that have shaped the Earth's surface, and there are no books that reveal their secrets. Our pages are the layers of sedimentary rocks, which deposited long ago at the bottom of the ocean. And these rocks encode in them the story of the Earth system. And we measure their physical and chemical properties, and from these, we learn a whole bunch of things: the chemical composition of the ocean and atmosphere, the activity of living organisms, and the climate that prevailed at different times in Earth history. And so today I'll share a story about a rusty record of deep time climate. I had the idea to develop and construct this record very shortly after starting at the Weizmann Institute in 2011. I got the right PhD student for it, an excellent student named Nir Galili, in 2013. And after 6 long years of developing methods, acquiring the samples, some of which are moving around the audience, in the field and from collaborators, and after weeks of experiments and measurements, we published a paper that put to rest one of the longest standing problems in modern geochemistry: the coupled history of Earth's climate and the oxygen isotope composition of Earth's oceans. So what exactly did we do? We collected samples of ancient iron-rich sedimentary rocks, like the ones moving around the audience, extracted the oxides, just like the rust on these chains, and measured their oxygen isotopes. And from these, we reconstructed Earth's climate going back 2 billion years. And that's about half the time that the oceans have existed, if you remember what Dudi told you earlier today. So our record did not come from these rusty chains, but from rocks that are called Uedel ironstones. And these are marine sedimentary rocks that are composed of these millimeter-sized, finely laminated concentric grains that we call ooids. And on the left, you can see one of our field sites in the Negev desert. And in the other pictures are optical or electron microscope images that show the often exquisite layering of the ooids. Now, the ooids are usually embedded in limestone or in flintstone, and NIR had to work very hard to develop protocols to separate the iron oxides from the other minerals in the rock. We got about 80 samples of Uedel ironstone from all over the world, and ages covering the present day to 2 billion years ago. And we measured their oxygen isotope composition and used this information to reconstruct the temperature in which they formed in the ancient oceans and the oxygen isotope composition of ancient seawater. And here's our temperature record now. Now let's walk through this. Time on the horizontal axis goes between the present day on the left and 2 billion years ago on the right. The temperature on the vertical axis is marked by these markers, and you can see that other than a brief period, relatively brief period, about 400 to 500 million years ago, Earth's surface temperature has been remarkably close to what it is today. And the profound implication here is that there are climate feedback mechanisms which on geological timescales of millions of years regulate Earth's surface temperature. This is a thermostat, if you will, that keeps the Earth's surface habitable with temperatures that are within a narrow range that's suitable for life. And in case some of you are thinking that this could save us from climate change, I'm sorry to disappoint. These are very, very slow processes, and humanity is emitting greenhouse gases at rates that are much, much faster than these processes can keep up with. As an aside, some of my other research is focused on accelerating natural processes to remove those greenhouse gases from the atmosphere at rates that are relevant to addressing the grand challenge of climate change, but that's a story for another day. I want to finish with a documented case where Earth's thermostat broke down, these so-called snowball Earth events. So about 720 million years ago, and then again about 650 million years ago, when life on the planet consisted only of microscopic algae and bacteria in the ocean, there's strong evidence that thick ice sheets covered all of the continents of that time. Now these episodes are not the ice ages that I'm sure you've heard about, which happened over the past few millions of years, and where the amount of ice was about double what it is on Earth today. These so-called snowball Earth events were mega ice ages, in which it's thought that the Earth completely froze over. The entire surface was ice covered. They occurred 600 to 800 million years ago, and they lasted for tens of millions of years. And you can think about them as episodes that are more than 10 times longer than the entire existence of hominids, where the Earth from space would have seemed like a ball of ice. And of course, this has captivated the imaginations of generations of geoscientists. But despite decades of research, there are still some basic questions about the total amount and the type of ice, how it formed, and perhaps most burning of all, life obviously persisted through these climate extremes, otherwise we would not be here in this auditorium, but how if the entire planet's surface was frozen? And so to address this, we got iron oxides from these very charismatic rocks that are called banded iron formations. We sampled such an iron formation, and by measuring the oxygen isotopes in those rocks and constructing what we call an isotopic mass balance, we were able to constrain the amount and the type of ice during the snowball. And what we found was very exciting. The oxygen isotopes appear to tell us contradictory stories. On one hand, the extent of glaciation is staggering. The possible states span a high ice case or a hard snowball, and a low ice case or a slush ball. And when I say that this is a low ice case, that's relative. Compared to the present day, where only about 2% of the Earth's water is frozen in ice caps on Greenland and Antarctica, 13% is a whopping big glaciation, which puts these extreme climatic episodes into perspective. Now, in the hard snowball, more than 30% of the planet's water froze. The thickness of ice on land was about 1,400 meters, and the oceans were covered by about 400 meters of ice. And in the slush ball, only about 13% of the oceans froze. The thickness of ice on land and over the oceans is about half as the hard snowball. But the really exciting finding that our results strongly suggest that evaporation from regions of open ocean occurred, both in the hard snowball and in the slush ball case. So on one hand, we have enough ice to cover the entire planet's surface, But on the other hand, there's a small fraction of the ocean that remained ice-free. And so our rusty records may help to explain how microorganisms persisted through these mega ice ages to have ultimately evolved into the rich biosphere that we see around us today.